All right, good morning, class. Welcome to this lesson on Electrostatics 3, Coulomb's Law. Today we will be able to define Coulomb's Law and understand how to set up some common problems. So Coulomb's Law. Coulomb's Law is the law that describes force between 2 point charges. 2 point charges. As you can see here, I have two charges, a positive and a negative. I have two charges here, a positive and a positive. So I have two specific charges. What is the force between these two charges specifically? Nothing else around it. Nothing else around it, just these two specifically. And the equation is this. F equals K, Q1, Q2 over R squared, where is a constant, K is a constant, and K is equal to 8.99 times 10 to the ninth newtons meters squared over Coulomb squared. So these charges Q1 and Q2 are Q1 and Q2 here, and they are measured in coulombs. Ours is measured in meters, and force is measured in newtons. So the first thing I want to point out about this is how similar it is to what we learned about gravity. Notice this is our equation for between 2 point charges, and if you remember our equation for gravity, F equals K m1 m2 over r squared. So you can see these are almost exact equations. It's just one uses mass and one uses charge. And except the really big difference is the value of K. If you remember from gravity, the value of K here was 6.67 times 10 to the negative 11th. Look at 10 to the negative 11th versus 10 to the ninth. These are huge differences, and this is why gravity is called a weak force. We consider gravity to be very strong because we can feel it every day. That's because the planet is huge. But the reality is electricity is way stronger than gravity, because you can see here from the K values that the force between two charges is going to be very, very strong. So we have our value here, our formula for charge here, and our formula for gravity here. Now, some common things you're going to run into. Actually, before I do that, let's stick to gravity for a second. Another major difference between these two is gravity is always attractive. Gravity is always attractive, meaning it always is going to attract two masses, whereas this force can be attractive or repulsive. Attractive or repulsive. As you can see, based on the charge, if they're opposite charges, they're going to attract to each other, and if they're the same charge, they're going to repulse each other away. So I want to cover that real quick. So now some common problems. One thing you're going to see often is if you have two charges that are the same. We have the same charges. We have the same charge on two charges, and we're trying to figure out what those charges are. So same charge, what is it? And so we know, so we're going to have F equals K Q squared over R squared, because Q1 equals Q2 because they are the same charge. So this is a very common thing you're going to have to do all the time. Notice from a conceptual base, from a conceptual understanding of this, that this law, F equals K Q1 Q2 over R squared, that we have the inverse square law here. We have the inverse square law, meaning distance greatly affects the force, okay? And that Q and Q1 or Q2 are directly related to F. So if these go up, F goes up. If these go down, F goes down. So it's going to be very common for you on a test that if they say if Q2 goes up by 3 and R2 goes down by 2, what's going to be our new force? And so you're going to have to figure that out based off just conceptual understandings. This is going to be something something we've done commonly throughout the whole year, so that should be something you're very used to. Okay, so notice that it is you're gonna have a lot of conceptual questions like that. Okay, some other things you're gonna see is you're gonna see charges on a line, or in one dimension, charges on a line in one dimension. And so notice here, Notice here we have Q1, Q3, and Q2. Based on their charge, this is positive, this is negative, this is negative. So if you look at it, we have a free body diagram right here. So we're going back to free body diagrams. Okay, so because these two negatives are both pulling on Q1, the charge from Q2 is going to pull it to the left. You can see that here, and the charge from Q3 is going to pull it to the right. And so um, because of this, it might ask you for the net force. They might ask you for the net force. Well, you would have to calculate the force of F1 and 2. You would have to calculate the force of F1 and 3 here. And then based off these two numbers, you would have to subtract these two. Subtract to find out what the net force is, and you can tell it's going to be in that direction, like this. Okay, so notice we have free body diagrams here, we have forces, and some of these forces are going to cancel out. Some of these forces are going to cancel out, okay, based off their position. All right, so that's a very common thing we did in mechanics a while ago, but now we're applying it to charges. A couple other things based on this problem. Notice we have -7 UC. What is that about? Mu stands for micro. Micro. So this is a microcoulomb. Microcoulomb. You're going to see this. You're going to see this very often. Just like in our section on light, we saw nanometers very often. Now we're going to see micro very often in charges. And micro is 10 to the -6. So you have to plug in 7 times 10 to the -6 for this problem here, or -7 times 10 to the -6 for this problem here. Okay, so you're going to see that a lot. So get used to that. Get used to that little symbol. And notice here, we are solving for forces. We are solving for forces. So if I have a force, if I solve for a force here and I get a certain number of newtons, I'll say, I don't know, 10 newtons, just to be simple. Notice that F equals MA, and if F equals 10 newtons, well then I can set that equal to MA. And so get used to your equation sheet, because if we're talking about charges or we're talking about electrons or protons, you need to know the mass. You need to know the mass of an electron, the mass of a proton, or the mass of a neutron, depending on what we're doing. So, and those you can find in any book. Like for example, the mass of a electron is 9.11 times 10 to the -31 kilograms. Okay, so you're going to be using a lot of scientific notation in these examples as well. So everything we did with forces and mechanics before, we can now apply to charges, which I know you're very excited about. Another thing, let's say very common, we have a proton and we have an electron, negative, going around the proton. We know the charges on each one of these. We know the charges, we'll say it's, actually forget that. We know the charges on these. We want to know how fast it's moving. How fast this is moving. Well, this is moving in a circle, so this is centripetal force. So we can set our equation K Q1 Q2 over R squared equal to M v squared over r, because this electron is moving in a circle. So just like we were able to set forces equal to each other in mechanics, we can take all those same things we learned and apply it here. We can solve for mass, we can solve for velocity, we can solve for distance, we can do all those things, okay, based off this law. And so we're gonna have to doing a lot of mechanics review as we go through this unit. Last thing, we can have charges in 2 dimensions, charges in 2D. So here's a very common example, and this example is looking at what is going to be the force on this charge Q1. Well, this one is negative, and so it's going to pull it towards it. This one is negative, it's going to pull it towards it. And you can see that from this free body diagram right here. This one's pulling it up, this one's pulling it to the side. But it's in 2 dimensions. It's in 2 dimensions. So because there is an angle here, we have to figure out what those angles are. And you can see right here that we have to break each one of these down. We have to break this force down, F12, into its x and y components, and then from there we would have to add the x and y components to each other. We're going to have to make triangles and do x and y components and then add those 2 components together. You might see an example where we have an equilateral triangle, also very common, something we're going to work on in class. So let's say this is positive, and this is negative. what's going to be the force on this, on, we'll say this one right here? Well, the negative is going to pull it this way, the positive is going to push it that way, and so the net force is going to be something like this, somewhere that way, and we have to calculate these numbers here. Okay, or we might see charges in a square, and if it's, positive, 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 negative, and we're looking at this one right here, this one's going to push it that way, this one's going to push it that way, and this one's going to pull it that way. And so we have to calculate all these and add them together. We have y here. This is all y component. This is all x component. And then we have to break this one down into its x and y components and then add them together and see what we're left with. So as you can see, we're going to be doing a lot of math, and it's going to be fun.